Hello everyone, welcome back to 3 Deviations. Today we are going to be talking about differentiation. We're really going to introduce some of the topics and some of the intuition behind differentiation, and we'll do a couple examples from physics. We'll get into the nitty-gritty rules later on in future videos. Let's get started. So we're going to begin with a little bit of a history lesson. So Isaac Newton was really one of the founding fathers of calculus, and he was the English physicist who discovered the derivative. He was also the guy who had the apple fall on his head. But that's not really important. What is important is what he wanted to find, which was the instantaneous velocity. So in physics, when we have a position versus time graph, the slope is our velocity, the slope of that graph, and sometimes that graph is a curve. So in order to find the velocity, the instantaneous velocity, you need to find the instantaneous slope, also known as the line tangent to the curve. Now, he could approximate it, but that isn't good enough for his calculations. So we can all approximate it using our little slope formula. So say we have this parabola, we could use these secant lines to approximate the slope, but we're not going to get to the exact tangent line that we want to reach. But what Isaac Newton found a way to do is to find the tangent line, to find the line that just skims the top of the graph. And that's exactly what he wanted to do in order to find instantaneous velocity. So how did he arrive at this? So what he did was he took the formula that we normally learn in high school that finds us the secant line, and that is f of b minus f of a over b minus a. And he asked the question, what if the difference between b and a was 0? So I thought, what if the difference between b and a was 0? Maybe I could use some limits. And he arrived at something that looked very similar to the difference quotient, but with a limit on it. So he found that the limit as h approaches 0 of f of x plus h minus f of x over h is the formal definition of the derivative. That means that with this formula, we can find the slope of a line tangent to a curve of functions. And that's pretty cool. And with this formula, we can do that, but as you can probably tell, once we get some like polynomials or rationals, this problem might be kind of tedious. So what we're going to do later is we're going to find all these helpful rules that are going to make it a lot easier, but that's coming later. Now let's talk about some derivative notation. So the classic notation is called Leibniz notation. That's just the classic d over dx for our difference over our little difference in x. And there are other types of notation. There's dy dx, df dx, or f prime of x. F prime of x is pretty popular. And sometimes people will write y prime. Some physicists will do y dot or theta dot, depending on what they're talking about. And there's also higher derivatives. So if I take a derivative of a derivative, well, then I have a second derivative. And if I want to take another, then I have a third derivative. And we can keep going on and on and on as long as our function allows it. So for that type of notation, we have d squared y over dx squared, or f double prime, and that's for second derivatives. But if we want to go to the nth derivative, we do dny over dxn, and that's also fnx. And writing out all these primes could become kind of tedious as we get to higher and higher derivatives, so we can just write the number derivative as our superscript. All right, so before we jump into an example, we're going to talk about differentiability. So if a function is differentiable at a, it is also continuous at a. So a function could be continuous at a, but it might not be differentiable at a. So let's take an example. Say I have f of x is equal to the absolute value of x. So that's going to look something like this. And if I want to take the derivative here, well, how am I going to take a tangent line here? There's nothing tangent to that. That's a jagged point. It's the thing. You cannot take the derivative at a jagged point. So that is a no-no for differentiability. I think also you cannot take the derivative at a vertical line as well. So that is differentiability. Now let's talk about finding the derivative. So this is going to be our first example, but this is just going to be pure math here. We're not going to do a word problem until later. So let's find the derivative of 5x cubed. So what we're going to do is we're going to take that difference quotient that we saw a couple slides ago, and we are going to plug in our function. So we're going to get the limit as h approaches 0, of 5x plus h cubed minus 5x cubed over h. Then we're going to expand that, and we'll get the limit as h approaches 0 of 5x cubed plus 15x squared h plus 15x h squared plus 5h cubed minus 5x cubed all over h. Now what we're going to do, we're going to combine all the like terms, and then we're going to divide by h. We're going to get this. We're going to get the limit as h approaches 0 of 15x squared plus 15xh plus 5h cubed. What we can do now, because h is going to 0, we can chop off the 5h cubed and the 15xh. And our limit will just come out as 15x squared. That is the derivative of 5x cubed. So if I want to find the derivative, if I want to find the tangent line, the slope of the tangent line to 5x cubed, I'm just going to take the value of x, then plug it into 15x squared, and then I'll get the slope. Alright, so now let's do a word problem. I did promise we'd do one later. So this one is going to involve a little physics. So if a car has a position function of x of t equals 10 plus 25.8t minus 4.9t squared, what is the velocity at t equals 3? So let's remember that the second derivative of the position function is equal to the first derivative of the velocity function, which is equal to the acceleration function. So in order to find the velocity, we're going to need to take the derivative of x of t, find x prime of t. So we are going to take the limit as h approaches 0 of that there, when we plug that into our difference quotient. And after that, we are going to expand, and then we will consolidate our like terms, and then divide by h, giving us dx dt, or v of t, is equal to 25.8 minus 9.8t. And if we plug in for v of 3, we will get negative 3.6 meters per second. So that is the first part of our problem. Now let's go to the second part of our problem. So now they're telling us to find the acceleration at t equals 5. And we are told to remember that the acceleration function is equal to the first derivative of the velocity function. So we just found the velocity function. So now we are going to take the derivative of that again, and we are going to get the limit as h approaches 0 of 25.8 minus 9.8t plus h minus 25.8 minus 9.8t over h. We're going to do what we've always done. We're going to expand, and then we are going to consolidate and divide by h, and we will get d squared x over dt squared, or dv dt, or a of t, is equal to negative 9.8. Students of physics will recognize that as the acceleration due to gravity. And if we plug in a of 5, we will get negative 9.8 meters per second squared as our acceleration. So that is it for the introduction to differentiation. This hopefully gave you some intuition behind differentiation. Next time we will be talking about the power rule and how that can help us with polynomials. See you then. Goodbye.